Google's new quantum chip did something that sounds almost impossible. It completed a calculation in under 5 minutes that would take the fastest classical supercomputers on Earth around 10 septillion years to finish. That is not just longer than human history. It is longer than the age of the universe by a scale so absurd that the number stops feeling real. The chip is called Willow, and on the surface, it looks like a breakthrough in computing. But beneath the headline is a question far stranger than speed. Where did all that computational power come from? Because some physicists believe quantum computers may not simply calculate inside our universe. They may process possibilities across many branches of reality at once. And if that interpretation is even partly true, then Willow may not just be a faster machine. It may be the first real technology that forces us to ask whether parallel universes are not fiction, but part of how computation itself works. Willow is a 105-qubit quantum processor, and that number matters. Classical computers use bits, zeros, and ones like tiny switches turning on and off. Every image, message, calculation, and video on the internet is built from those simple binary decisions. Quantum computers use qubits, and qubits do not behave like ordinary switches. They can exist in multiple states at once through superposition. And when they become entangled, the system can process an enormous number of possibilities simultaneously. That is why Willow's achievement feels so unreal. It was given a random circuit sampling benchmark, a task designed to test whether a quantum machine can generate outputs from extremely complex quantum patterns. For a normal supercomputer, this problem becomes almost absurdly difficult. Not difficult like a hard exam. Difficult like asking a person to count every grain of sand on every beach on Earth, then repeat the process for longer than the universe has existed. Willow did it in less than 5 minutes. This is why people are calling it a new moment of quantum supremacy. Google made a similar claim in 2019 with Sycamore, but that result was challenged. Some argue that better classical algorithms could reduce the gap. Willow feels different because the gap is not merely large. It is astronomical. The comparison is so extreme that it makes classical computing look like it is playing a different game entirely. But the deeper story is not the benchmark itself. It is what the benchmark implies. If a small chip can explore a computational space so vast that classical machines cannot reach it in any meaningful amount of time, then we have to ask what a quantum computer is really doing when it calculates. And that question opens a door most people thought belonged only to science fiction. Quantum mechanics has always been strange. A particle can exist in several possible states until it is measured. A system can behave like it contains multiple outcomes at once. Then when we observe it, we see only one result. For decades, physicists have argued about what that really means. One interpretation says those other possibilities are just probabilities. They do not physically exist. They are mathematical tools that help us predict what we will observe. But another interpretation, known as the many worlds interpretation, says something far more radical. It says the other possibilities do not vanish. They continue in separate branches of reality. In one branch, a particle goes left. In another, it goes right. In one universe, the coin lands heads. In another, it lands tails. Every quantum event branches reality into multiple outcomes. All real, all existing, but separated from one another. Now, apply that idea to a quantum computer. When Willow processes a calculation, it does not test one possibility at a time like a classical computer. It manipulates many possibilities at once. In the many worlds view, those possibilities are not just abstract. They correspond to real branches of reality. That means the computation may be distributed across different versions of the universe with interference between those branches helping produce the final answer in ours. It sounds insane at first, but this idea has been defended by serious physicists for decades. And Willow's result makes the question feel urgent. Because if the machine completed in minutes what classical computers would need cosmic timescales to perform, then maybe the explanation is not simply that quantum computers are fast. Maybe they are not computing alone. Imagine a problem so complex that one person could never solve it. Not in a lifetime. Not in 1,000 lifetimes. Now imagine that infinite versions of that person across infinite rooms each solve a tiny part of it. Then somehow the useful parts of those answers interfere, combine, and collapse into one result that appears in your room. That is one way to visualize the many worlds view of quantum computation. Not perfect, but close enough to feel the strangeness. Willow may be like a switchboard connecting possibilities that ordinary reality keeps separated. It does not open a portal. It does not let us speak to another Earth. but it may use the mathematical structure of many realities to solve problems that no single classical system could handle. This is where the phrase parallel universes becomes more than a dramatic headline. In quantum computing, interference is everything. Possible outcomes reinforce or cancel each other until the correct pattern becomes more likely. If those possibilities are physically real branches, then the calculation is not just happening inside the chip. It is happening across the structure of reality itself. That is the idea that makes Willow so mind-bending. A chip in a laboratory could be exploiting the same deep rules that govern the branching of the universe. Every qubit becomes more than a unit of information. It becomes a doorway into a landscape of possibilities. And yet the final answer appears here in our branch on our screen, as if an unimaginable amount of hidden work happened somewhere we cannot directly see. But here is where the story needs honesty. Willow did not prove the multiverse. It did not detect another universe. It did not send information across realities or receive a message from a parallel Earth. The many worlds explanation is one interpretation of quantum mechanics, not a confirmed fact. The most widely taught interpretation, often called the Copenhagen interpretation, does not require parallel universes at all. In that view, quantum states are probability waves. A quantum computer is not borrowing power from other worlds. It is manipulating probabilities with extreme precision until the right answer emerges through interference. And there are other reasons for caution. Willow's achievement involved a benchmark task, not a practical real-world problem like curing cancer, cracking climate models, or designing a new drug. That does not make it meaningless. But it does mean we should understand what kind of milestone it is. It proves power in a controlled test. It does not yet prove everyday usefulness. There is also the challenge of scale. Willow has 105 qubits, which is impressive, but practical fault-tolerant quantum computing may require far more. Quantum systems are fragile. They are sensitive to noise, heat, vibration, and tiny environmental disturbances. Google's progress in error correction is important because it suggests the machines are becoming more stable. But the road from a record-breaking benchmark to a universal quantum computer is still long. So the truth is both exciting and unsettling. Willow may not prove we tapped into parallel universes, but it makes the question harder to ignore. It forces us to confront the possibility that quantum computing is not just a new kind of engineering. It may be a clue about what reality really is. The part most people miss is that Willow's real breakthrough may not only be speed. It may be stability. Quantum computers are famously fragile. A tiny vibration, a slight temperature change, a stray electromagnetic disturbance, and the information inside the qubits can collapse before the calculation is complete. This is why quantum computing has always felt like trying to build a cathedral out of smoke. The theory is beautiful, but the structure keeps falling apart. That is why error correction matters so much. A useful quantum computer cannot simply be powerful. It has to be reliable. It has to protect quantum information long enough to perform meaningful calculations. And Willow showed progress in exactly that direction. Instead of errors becoming worse as the system scaled, Google demonstrated techniques designed to make the machine more stable as it grows. That is a major signal because if quantum computers can scale while reducing errors, then they stop being laboratory curiosities and start becoming real machines with world-changing potential. Drug discovery could accelerate. New materials could be designed atom by atom. Climate systems could be modeled with a level of detail classical computers cannot reach. Encryption could be transformed or threatened entirely. But underneath all of that practical promise is the stranger question. If quantum error correction allows a machine to preserve superposition and entanglement for longer, then we are learning how to keep the quantum world open. We are learning how to maintain the fragile state where many possibilities coexist before reality chooses one. And if many worlds is right, then every improvement in error correction is not just better engineering. It is better control over the boundary between branches of reality. This is why Willow matters even if it does not prove parallel universes today. It points toward a future where quantum machines become powerful enough to make old debates impossible to ignore. For almost a century, physicists have argued about what quantum mechanics really means. Are probabilities just mathematical tools? Does reality collapse when observed? Do all possible outcomes continue in other branches? For decades, these questions felt philosophical because the experiments were too small to force the issue. But machines like Willow change the scale. When a quantum chip performs calculations beyond the reach of classical supercomputers, those interpretations stop feeling abstract. The machine becomes a physical question, a device sitting in a laboratory asking us what kind of universe could allow this to happen. Maybe the answer is purely mathematical. Maybe quantum computers are simply better at manipulating probability than anything we have ever built. Or maybe they are evidence that reality is far larger than the single branch we experience. Maybe every quantum calculation is a tiny conversation between possible worlds, and we are only now building machines sensitive enough to use that conversation. Either way, Willow is not just a chip. It is a warning that computation is about to become cosmology. The next generation of quantum processors may not only change technology, they may change the way we define reality itself. And if Google has already reached this point with 105 qubits, then the question is not whether quantum computing will become more powerful. The real question is what we will discover when it does. And that is why Willow feels different. It is not just another processor. It is not just another step in the race between Google, IBM, Microsoft, and the rest of the quantum world. It is a machine that forces us to ask a question we may not be ready to answer. Where does quantum computation really happen? Maybe the answer is simple. Maybe Willow is only manipulating probability with extraordinary precision. Maybe there are no parallel universes involved at all. Maybe the multiverse is still only an interpretation, beautiful, strange, but unproven. But maybe not. Maybe the reason quantum computers seem impossibly powerful is because reality itself is not singular. Maybe every calculation opens a hidden landscape of possibilities, and the chip does not create those possibilities. It simply learns how to use them. That is what makes this so unsettling. Willow did not prove that parallel universes exist, but it brought the question closer to the lab than ever before. It turned an idea once trapped in philosophy and science fiction into something connected to real hardware, real measurements, and real results. And if this is only the beginning, then future quantum chips may do more than solve impossible problems. They may reveal that the universe is not one story, but many stories unfolding at once. So the real question is not whether Google built a faster computer. The real question is this: did we just build the first machine capable of touching the edges of other realities? And if discoveries like this fascinate you, make sure to subscribe, because the future of quantum computing may not only change technology, it may change what we mean by reality itself.